Far out in the depths of space, where light takes centuries just to whisper its arrival, there's a place where stars are born, a cosmic forge where swirling clouds of gas and dust ignite into blinding beacons of raw power. Picture a single point in that vast nebula, where gravity's relentless pull collapses matter into a furnace so intense, it births a star capable of outshining entire galaxies. This isn't just any star. This is one of the universe's elite, a titan among titans, where the rules of physics warp under the weight of its brilliance. And believe it or not, it's just one of the 30 most powerful stars we're about to explore. What makes a star truly powerful is its sheer size, temperatures hot enough to vaporize planets in seconds, or the way some of them die in explosions so violent they briefly outshine every other light in the cosmos. The answer is all of that and so much more. These aren't just distant points of light, they're the universe's extreme athletes breaking records and defying expectations. Some are so massive they make our sun look like a speck of dust. Others spin faster than a blender on its highest setting, flinging storms of energy across space. And a few are so strange they challenge everything we thought we knew about how stars live and die. This journey isn't just about listing stars, it's about uncovering the stories behind their power. How a single star can shape entire galaxies, how its death can seed the universe with the very elements that make life possible, and how, even from millions of light years away, these celestial giants remind us of just how small and how connected we truly are. So buckle up. By the time we're done, you'll see the night sky not as a quiet blanket of twinkling lights, but as a raging, dynamic arena where the most incredible stellar heavyweights battle for supremacy. And trust me, what you're about to discover will change the way you look up forever. Meet UY Scuti, the reigning heavyweight champion of size in the known universe. If our sun were a marble, this star would be a stadium so vast that over 1.3 million Earths could fit inside it. Nestled in the Scutum constellation, this red hypergiant stretches so wide, its surface would swallow our entire solar system out past the orbit of Jupiter. That's a diameter of around 1.7 billion miles, a scale so immense it defies earthly comparison. But here's the twist: despite its mind-bending size, UY Scuti isn't the hottest or brightest star we'll encounter. Its surface simmers at just around 3,000 Kelvin, cooler than our sun's scorching 5,700, yet its power comes from sheer volume. Imagine a bonfire next to a blowtorch. The torch is hotter, but the bonfire radiates far more total energy simply because it's enormous. That's UY Scuti. It pumps out over 340,000 times more light than our sun, not because it's intensely fiery, but because there's just so much of it burning all at once. What's even wilder, this star is unstable, pulsating like a slow-motion heartbeat. Its outer layers are so loosely held by gravity, they're practically bubbling away into space, creating a hazy cocoon of lost material. Astronomers think it's already shed multiple suns' worth of mass, and it's nowhere near done. In cosmic terms, UY Scuti is living on borrowed time. Within the next few million years, it'll likely explode in a supernova so bright, it'll outshine entire galaxies for weeks. Until then, it stands as a humbling reminder: in the universe, raw scale alone can redefine what power looks like. UY Canis Majoris isn't just a star, it's a cosmic drama unfolding in real time. Located in the constellation Canis Major, this hypergiant is so colossal, it makes most other stars look like specks. If placed at the center of our solar system, its surface would extend beyond the orbit of Saturn, engulfing everything in its path. But size isn't even its most striking feature. What sets UY Canis Majoris apart is the sheer violence of its existence. This star is essentially tearing itself apart. Every year, it ejects vast amounts of material enough to form multiple planets in titanic eruptions. Imagine a volcano, but instead of lava, it's spewing out enough gas and dust to create an entire nebula. In fact, the star is already surrounded by a sprawling cloud of its own debris, a nebula forged from its own explosive tantrums. These outbursts aren't just occasional, they're constant, driven by a turbulent atmosphere where convection currents churn like a storm that never ends. And yet, for all its ferocity, UY Canis Majoris is living on borrowed time. Hypergiants like this burn through their fuel at an astonishing rate, and this one is no exception. In astronomical terms, it's already on the verge of collapse. When it finally runs out of fuel, it won't just go quietly. The most likely outcome, a supernova so powerful it could rival the brightness of an entire galaxy. Some scientists even speculate it might go a step further, triggering a hypernova, an explosion so cataclysmic it would unleash a deadly burst of gamma rays across space. But here's the twist: even in death, UY Canis Majoris would shape the cosmos. The elements forged in its core and scattered by its explosion would become the building blocks of future stars, planets, and possibly even life. It's a reminder that destruction and creation are two sides of the same cosmic coin, a cycle as old as the universe itself. Look up at Orion's shoulder and you'll spot Betelgeuse, a roiling red supergiant that's anything but stable. This star doesn't just burn, it throws cosmic tantrums. In late 2019, astronomers watched in shock as Betelgeuse dimmed dramatically, losing nearly 2/3 of its usual brightness. For months, the internet buzzed with speculation. Was this the prelude to a supernova? Turns out, the star had coughed out a colossal cloud of dust, temporarily veiling its light. But that event was a mere hiccup in Betelgeuse's chaotic life. What makes this star so fascinating isn't just its erratic behavior, it's the sheer inevitability of its demise. Betelgeuse is running on empty. In stellar terms, it's already in its death throes, having burned through its hydrogen fuel and now fusing heavier elements in a desperate bid to stay alive. And when it finally collapses, the show will be unforgettable. A supernova from Betelgeuse would outshine the full moon, visible even in broad daylight for weeks. Ancient civilizations might have witnessed such an event, like the supernova of 1054, recorded by Chinese astronomers as a guest star brighter than Venus. But Betelgeuse's explosion would be closer, brighter, and rarer, a once-in-a-millennium spectacle. Yet here's the twist: despite its impending doom, Betelgeuse plays a vital role in the cosmos. Its violent winds have already seeded nearby space with carbon, oxygen, and other elements crucial for life. And when it explodes, the shockwave will trigger new star formation in its wake. Even in death, this supergiant won't just vanish, it'll reshape its corner of the galaxy. So while we might not see it go supernova in our lifetimes, Betelgeuse reminds us that stars aren't just distant lights. They're actors in an epic, ever-unfolding drama, one where destruction births new beginnings. Shifting our gaze from the fiery red supergiants, we come to Rigel, a searing blue beacon that dominates Orion's celestial footprint. This isn't just another bright star, it's a blistering powerhouse radiating energy at a rate 40,000 times greater than our Sun. If the Sun were a candle, Rigel would be a stadium floodlight, its brilliance so intense it can cast shadows on Earth even from over 800 light-years away. What makes Rigel so extraordinary isn't just its luminosity, it's the ferocity behind that glow. Blue supergiants like this are stellar furnaces burning at temperatures exceeding 12,000 Kelvin, nearly twice as hot as our Sun. Their energy doesn't gently radiate, it erupts, propelled by stellar winds that roar outward at speeds topping 2 million miles per hour. These winds don't just stream into space, they sculpt it. Around Rigel, they've carved vast bubbles in the surrounding nebula, pushing gas and dust into intricate structures that glow under the star's relentless ultraviolet assault. Yet Rigel's dominance comes with a caveat: it's a cosmic rarity. Stars this massive and luminous are fleeting giants, accounting for less than 1% of all stars in the universe. Their lives are spectacular but short, a few million years compared to the Sun's 10 billion. Rigel's fate is already sealed. One day, it won't just fade, it'll detonate, likely collapsing into a neutron star or black hole while seeding its surroundings with the heavy elements forged in its core. For now, though, it stands as a testament to the universe's capacity for extremes. A blue supergiant so powerful, it doesn't just light up Orion's foot. It defines it. Eta Carinae isn't just a star, it's a cosmic powder keg with a fuse that's been burning for centuries. Lurking in the Carina constellation, this luminous blue variable star is one of the most unstable objects in the Milky Way, a celestial rebel that refuses to play by the rules. What makes it unforgettable isn't just its staggering brightness, over 5 million times more luminous than our Sun, but its history of violent outbursts. In the 1840s, Eta Carinae staged a performance that stunned astronomers worldwide. Without warning, it erupted in an event now called the Great Eruption, catapulting it to become the second brightest star in Earth's night sky, outshone only by Sirius. For over a decade, it blazed with the intensity of a cosmic flare, then just as mysteriously faded back into obscurity. The aftermath of that explosion is still visible today. Eta Carinae didn't just dim, it sculpted its own tomb. The star is now cocooned within the homunculus nebula, a bizarre, hourglass-shaped cloud of gas and dust ejected during the eruption. This bipolar structure, stretching over half a light-year across, is like a fossilized scream, preserving the violence of that event in stunning detail. Hubble's images reveal intricate tendrils and knots within the nebula, each a testament to the star's turbulent temper. But here's the chilling part: the Great Eruption might have just been a warm-up. Eta Carinae is a prime candidate for one of the universe's most cataclysmic events, a hypernova. Unlike a regular supernova, which marks the death of a star, a hypernova is a stellar apocalypse. It's thought to occur when an exceptionally massive star collapses into a black hole, releasing a gamma ray burst so intense it could sterilize planets light years away. Eta Carinae's sheer mass, over 100 times that of our Sun, makes it a ticking time bomb. When it finally detonates, the energy released could outshine an entire galaxy, at least briefly. Yet even in its current state, Eta Carinae is far from quiet. It's prone to smaller eruptions, belching out jets of material at near relativistic speeds. Its winds, racing at millions of miles per hour, collide with older debris, creating shockwaves that glow in X-rays. And lurking at its core is likely a binary companion, a second star locked in a deadly dance that may have triggered past outbursts and could ignite future ones. What's perhaps most humbling is that Eta Carinae's fate is already sealed. The only question is when. In cosmic terms, its explosion could happen tomorrow or in 100,000 years. But when it does, it won't just be a spectacle. It'll be a transformative event, seeding the galaxy with heavy elements and possibly altering the chemistry of nearby star-forming regions. Eta Carinae reminds us that the universe isn't just vast, it's volatile, capable of rewriting its own rules in an instant. And for now, we're lucky enough to have a front-row seat to its rebellion. Hidden in the constellation Sagittarius, WR102 isn't just a star, it's a runaway cosmic blowtorch, burning so fiercely it redefines the limits of stellar violence. While most stars shine through relatively peaceful fusion, this Wolf-Rayet class object is essentially tearing itself apart at hyperspeed. Its surface simmers at over 200,000 degrees Celsius, so hot it makes blue supergiants like Rigel seem almost cool by comparison. At that temperature, matter doesn't just glow, it radiates brutal ultraviolet and X-ray energy that would strip apart any planet foolish enough to orbit it. But the real shocker isn't the heat, it's the hurricane-force winds screaming off its surface at 2,000 kilometers per second. That's nearly 1% the speed of light, fast enough to cross the Atlantic Ocean in under 2 seconds. These aren't gentle breezes, they're supersonic tsunamis of ionized gas, blasting outward with enough force to strip away entire solar masses worth of material in just a few thousand years. Picture standing in front of a cosmic sandblaster, except instead of sand, it's superheated plasma moving faster than a bullet. That's the daily reality for WR102, a star so volatile, it's literally evaporating before our eyes. What makes this Wolf-Rayet star truly bizarre, though, is what it's spewing into space. Unlike most stars that exhale hydrogen or helium, WR102's winds are laced with oxygen and carbon, ash from nuclear fusion happening at breakneck speed deep in its core. This rare oxygen-rich spectrum is like a chemical fingerprint, revealing a star that's already burned through its lighter elements and is now cannibalizing its own remains. It's the cosmic equivalent of a house burning so hot, it's consuming its own foundation. And here's the kicker, this can't last. WR102 is on borrowed time, likely just decades or centuries away from total collapse. When its core finally gives out, the implosion won't be a slow fade, it'll be one of the universe's most spectacular fireworks shows. Current models suggest it could produce a gamma-ray burst, a beam of energy so focused and powerful, it could outshine entire galaxies for a split second. Even more chilling, if that beam were pointed at Earth, despite being over 8,000 light-years away, the radiation could potentially strip our ozone layer. Thankfully, WR102's axis seems tilted safely away from us. For now, this star serves as a stark reminder, the universe doesn't just create. It annihilates, reinvents, and pushes matter to extremes we're only beginning to understand. WR102 isn't just dying, it's going out in a blaze of fury so intense, it'll briefly outshine everything else in its galactic neighborhood. And in that final flash, it'll forge the very elements that might one day seed new stars, planets, or even life. Some endings aren't quiet, they're revolutions. Deep within the dense stellar jungle of our galaxy's core, where stars pack together like fireflies in a jar, one particular giant stands apart, not just for its brilliance but for its sheer audacity. Meet the Pistol Star, a luminous monster lurking just 100 light-years from Sagittarius, a star, the supermassive black hole anchoring the Milky Way. This star doesn't just shine, it dominates, blasting out 1.6 million times more energy than our Sun, a figure so staggering it would take our Sun an entire month to emit what the Pistol Star unleashes in a single second. Its name comes from the eerie, pistol-shaped nebula surrounding it, a cosmic silhouette carved by the star's own violent eruptions. Imagine a celestial gunslinger firing off rounds of stellar material instead of bullets. Over the past few thousand years, this hypergiant has ejected enough gas and dust to form 10 suns, creating that distinctive nebula in its wake. But unlike a revolver that runs out of ammunition, the Pistol Star shows no signs of stopping. Its winds scream outward at nearly 100 kilometers per second, stripping away layers of its own atmosphere in a relentless stellar tantrum. What makes this star even more extraordinary is its birthplace. Nestled in the quintuplet cluster, a swarming hive of massive stars near the galactic center, it endures conditions unlike anywhere else in the galaxy. Here, gravitational tides from nearby stars and the ever-present pull of Sagittarius, a star, create a pressure cooker of cosmic forces. Most stars wouldn't survive this environment, but the Pistol Star isn't just surviving, it's thriving, burning with a ferocity that defies logic. Yet its brilliance comes at a cost. Hypergiants like this one live fast and die young. The Pistol Star is likely less than 3 million years old, yet it's already on borrowed time. With a mass somewhere between 80 to 100 times that of our Sun, it's hemorrhaging material so quickly, astronomers estimate it's lost the equivalent of 30 solar masses already. That's like shedding an entire sun's worth of material every 100,000 years, a rate so extreme, it reshapes our understanding of how stars lose mass. And when its end comes, it won't be quiet. Current models suggest it's destined for a pair instability supernova, a runaway thermonuclear explosion so violent it obliterates the star completely, leaving no black hole or neutron star behind. Just a fleeting, galaxy-spanning flash of light, and then nothing, no remnant, no corpse, pure annihilation. For now, though, the pistol star continues its reckless dance, a beacon of excess in the galactic core. It serves as a stark reminder, in the universe, even the brightest flames burn out the fastest, and when they do, they don't just fade, they rewrite the rules on their way out. R136A1 isn't just a star, it's a cosmic anomaly that rewrites the textbooks. Nestled within the Tarantula Nebula, a sprawling stellar nursery in the Large Magellanic Cloud, this behemoth tips the scales at 265 times the mass of our Sun. To put that into perspective, if our Sun were a golf ball, R136A1 would be a wrecking ball so massive it shouldn't theoretically exist. Current models of star formation once insisted that stars couldn't surpass 150 solar masses without tearing themselves apart. R136A1 laughs in the face of those limits, but its mass isn't even its most staggering feature. This star burns with the fury of 8.7 million suns, a luminosity so intense, its ultraviolet radiation alone could shred nearby gas clouds before planets even had a chance to form. If placed at the center of our solar system, its surface would extend beyond Mercury's orbit, and its light would vaporize Earth within seconds. The energy it emits in 1 second would power human civilization for over 300,000 years. The Tarantula Nebula, its chaotic home, is the perfect cradle for such a monstrosity. This region is a frenzied hub of star birth, where dense gas clouds collapse under their own gravity at breakneck speeds. Here, stars don't just form, they collide, merge, and cannibalize each other in a cosmic free-for-all. Some astronomers suspect R136A1 might be the product of such a stellar merger, a Frankenstein's monster stitched together from smaller stars. Others argue it could have grown this massive by sheer luck, hoarding gas from its surroundings faster than the radiation pressure could blow it away. Yet R136A1's existence isn't just a puzzle, it's a time bomb. Stars this massive live fast and die young, burning through their fuel in just a few million years. When it finally collapses, it won't just go supernova. It might trigger a pair instability explosion, a runaway thermonuclear detonation so powerful, it obliterates the star entirely, leaving no black hole behind, just a void and a temporary blaze brighter than entire galaxies. For now, R136A1 stands as a cosmic rebel, defying our understanding of how stars are born and how big they can grow. It's a reminder that the universe doesn't play by our rules, it writes its own. And in the Tarantula Nebula's tangled web, it's spinning a story we're only beginning to unravel. Stephenson 218 doesn't just break records, it shatters them. Imagine a star so colossal, it makes UY Scuti, once the undisputed king of stellar size, look almost modest by comparison. Recent observations suggest this red hypergiant, nestled within the distant Stephenson 2-star cluster, stretches over 2,000 times the radius of our Sun. If placed at the center of our solar system, its surface would engulf Saturn's orbit, leaving no room for the inner planets, just an ocean of churning plasma where they once orbited. But size isn't the only staggering thing about Stephenson 218. Its very existence challenges what we thought we knew about how stars grow. Most hypergiants this massive are unstable, shedding material so violently they'd never reach such extremes. Yet here it sits, a cosmic paradox glowing with a cool, ruddy hue, its surface a relatively chilly 3,200 Kelvin compared to the Sun's scorching 5,700. That's the irony of red supergiants. The bigger they get, the cooler they appear, like a bonfire spreading its heat thin across a vast expanse. What's even more fascinating is its home, the Stephenson 2 cluster, a tight-knit family of massive stars lurking near the galactic center. This region is a pressure cooker of gravitational forces and radiation, where stars jostle for space like commuters in a packed train. Most stars here live fast and die young, but Stephenson 218 has defied the odds, ballooning to dimensions that leave astronomers scratching their heads. Some theorize it's a product of multiple stellar mergers, a Frankenstein's monster stitched together by cosmic collisions. Others suggest it's simply the result of an insatiable appetite, a star that greedily hoarded gas from its surroundings faster than the usual limits would allow. Yet for all its grandeur, Stephenson 218 is a ticking time bomb. Stars this size don't get to grow old. Within a few million years, a blink in cosmic time, it'll likely collapse under its own weight, triggering a supernova so bright it could outshine entire galaxies. And when it does, the explosion won't just be a spectacle. It'll scatter heavy elements forged in its core across space, seeding future generations of stars, planets, and perhaps even life. For now, though, it stands as a humbling reminder. The universe has a way of upending our expectations. Just when we think we've found the limits of stellar size, along comes a star like Stephenson 218, stretching the boundaries of what we thought possible, and daring us to look up and wonder what else might be out there waiting to be discovered. Mu Cephei, known as Herschel's garnet star for its deep ruby glow, is a cosmic elder whispering its final verses. Unlike the searing blue infernos we've encountered, this red supergiant pulses with the slow, labored rhythm of a star nearing the end. Its color alone tells a story, a cooling giant, its surface temperature barely scraping 3,500 Kelvin, radiating a hue so rich 18th century astronomer William Herschel described it as garnet-tinted. But this star isn't just a pretty spectacle, it's a ticking time bomb bloated to over 1,000 times the sun's radius. If swapped with our sun, it would swallow everything out past Jupiter's orbit. What makes Mu Cephei especially fascinating is its instability. Like a flickering candle in a cosmic breeze, its brightness varies unpredictably, dimming and flaring over months or years. These pulsations aren't just surface quirks, they're death throes. The star's core, already layered like an onion with shells of fused helium, carbon, and oxygen, is racing toward collapse. Every convulsion sends shock waves through its bloated outer layers, ejecting plumes of dust that further dim its light. Ancient astronomers might have witnessed these very fluctuations. Some historians speculate that Ptolemy's star catalogue, compiled in the 2nd century, noted Mu Cephei's variability, an early record of a dying star's struggle. The clock is running out. Mu Cephei has maybe 100,000 years left, a mere heartbeat in cosmic terms. When its core finally exhausts its fuel, the collapse will trigger a type Roman II supernova, an explosion so brilliant it could outshine the moon for weeks. The aftermath, a neutron star or black hole, and a nebula glittering with the heavy elements forged in its final moments, carbon, oxygen, even gold. For now, Mu Cephei remains a garnet jewel in Cepheus, a reminder that even stars fade. But in its death, it'll seed the universe with the very ingredients for new worlds. The cycle continues, one stellar and becomes another's beginning. VFTS 682 is the cosmic equivalent of a lone wolf, a rebel star that defies the rules. Unlike most massive stars that cling to the safety of dense clusters, this brilliant outcast roams solo through the void of the Large Magellanic Cloud, some 160,000 light-years from Earth. Discovered by the Very Large Telescope in Chile, it wasn't just its isolation that stunned astronomers, it was its sheer power. With a mass 150 times that of our Sun and a luminosity over 3 million times brighter, VFTS 682 burns with a ferocity that rivals the most extreme stars in the universe. Yet here it sits untethered, like a king dethroned and cast into exile. So how does a star this massive end up alone? The leading theory is as dramatic as the star itself, a gravitational slingshot. Picture a crowded stellar nursery where young stars jostle for space like bullies on a playground. In this chaos, close encounters between massive stars can fling one of them outward at staggering speeds, up to hundreds of kilometers per second. For VFTS 682, that violent ejection might have been a survival tactic. In dense clusters, collisions between stars are common, and for a heavyweight like this, getting thrown clear could have spared it an even messier fate. But there's another possibility. Maybe VFTS 682 never had a home to begin with. Some models suggest massive stars can form in relative isolation, born from dense, collapsing gas clouds without the need for a bustling stellar neighborhood. If true, this challenges the long-held belief that stars this colossal require the intense pressure of a cluster to ignite. VFTS 682 could be proof that the universe has more than one recipe for forging giants. Its isolation isn't just a curiosity, it's a goldmine for science. Without the light pollution of nearby stars, astronomers can study its pristine stellar winds, its chemical makeup, and the fierce radiation it emits. Already, it's taught us that even solitary stars can wield unimaginable power. And when its short, fiery life ends in a supernova, it'll die as it lived, alone but unforgettable. The explosion will ripple through its corner of the galaxy, scattering heavy elements into the void, a final act of defiance from a star that never played by the rules. LBV 180620 isn't just another hypergiant, it's a celestial powerhouse with a hidden weapon, a magnetic field so intense it could rip atoms apart. Nestled near the chaotic core of the Milky Way, roughly 30,000 light-years from Earth, this star doesn't just radiate light, it wages war against itself. With a magnetic field clocking in at over 1,000 times stronger than Earth's, it's like comparing a refrigerator magnet to the force that holds neutron stars together. This isn't just unusual for a star of its class, it's downright revolutionary. Most luminous blue variables like Eta Carinae are already unstable, prone to violent outbursts that eject entire solar masses into space. But LBV 180620 takes chaos to another level. Its magnetic field acts like a cosmic straitjacket, channeling the star's eruptive energy into focused, high-velocity jets. Imagine a volcano not just erupting, but shooting laser-guided plumes of plasma into the void. These jets, twisted and accelerated by the magnetic field, can reach speeds of millions of miles per hour, carving pathways through the surrounding nebula like a cosmic blowtorch. And then there's the luminosity. Even by the standards of galactic giants, this star is obscenely bright, roughly 2 million times more luminous than the Sun. If placed in our solar system, its light would vaporize planets within weeks. But here's the twist, we can't even see most of that brilliance with our eyes. LBV 180620 is shrouded in thick clouds of dust, likely ejected during past eruptions. What little light escapes is stretched and reddened by interstellar gas, making it appear deceptively dim in visible light. Only infrared and radio telescopes can pierce the veil, revealing the monster beneath. What makes this star truly exceptional, though, is its neighborhood. The galactic center is a cosmic war zone, a region where stars orbit a supermassive black hole at breakneck speeds, where radiation and gravitational tides twist the rules of physics. Surviving here requires resilience, and LBV 180620 has it in spades. Some astronomers speculate its magnetic field might be the secret, a shield against the chaotic forces of its environment. Others think the star's extreme properties could be the result of that environment, as if the galactic center itself forged this magnetic freak of nature. One thing's certain, LBV 180620 won't live long. Stars this massive rarely do. In a few million years, it'll likely collapse in a supernova, or perhaps even a hypernova, leaving behind a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth. When that happens, the explosion won't just light up the sky. It'll send ripples through the fabric of spacetime itself, a final, defiant echo of the most magnetic star we've ever known. Until then, it stands as a reminder, even in a universe of extremes, there's always room for something stranger. Doradus isn't just a star, it's the gold standard for cosmic unpredictability. As the prototype of the luminous blue variable class, this celestial chameleon defines what it means to be unstable. Nestled in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, Doradus operates on a scale of extremes. Most stars flicker with minor brightness changes, but this one doesn't just vary, it reinvents itself, swinging between brilliance and obscurity like a cosmic pendulum. At its peak, it outshines a million suns. During its faintest phases, it dims to a fraction of that radiance. These aren't subtle adjustments, they're full-scale identity crises playing out over years or decades. What drives these wild fluctuations? The answer lies in the star's fragile grip on its own existence. Luminous blue variables like Doradus are so massive, somewhere between 50 to 100 solar masses, that they're perpetually on the verge of self-destruction. Their cores pump out enough energy to power small galaxies, but that radiation doesn't just flow peacefully into space. It battles against gravity, creating titanic pressure imbalances that destabilize the star's outer layers. Imagine a tea kettle boiling so violently, its lid rattles off intermittently, except here, the steam is entire layers of the star's atmosphere being ejected into space. The aftermath of these outbursts is what makes Doradus so visually striking. During a bright phase, the star swells to staggering proportions, its surface cooling and reddening as it expands. But when the eruptions come, they blast away material, forming vast shrouds of dust and gas that temporarily veil its brilliance. This cycle isn't just dramatic, it's self-perpetuating. Each eruption strips mass from the star, weakening gravity's hold and making the next outburst even more likely. Over millennia, Doradus has likely shed dozens of solar masses this way, transforming its surroundings into a nebula of its own debris. Yet for all its chaos, Doradus is a Rosetta Stone for astronomers. By studying its behavior, we've decoded the secrets of other LBV stars like Eta Carinae and P Cygni. Its fluctuations reveal the delicate balance between radiation pressure and gravity, teaching us why some stars flirt with self-destruction while others burn steadily. And its eruptions provide clues about the final act of these cosmic divas. Most LBVs end their lives not with a whimper but with a supernova, or if they're massive enough, a hypernova so powerful it briefly outshines the rest of the universe. Doradus reminds us that stars aren't static fixtures. They're dynamic, evolving entities capable of radical transformations on human timescales. And as the archetype of its class, it continues to challenge our assumptions, proving that in the cosmos, stability is the exception, not the rule. Rho Cassiopeiae isn't your average star. It's a tempest wrapped in golden light, a ticking time bomb masquerading as a celestial jewel. Among the rarest of stellar breeds, yellow hypergiants like Rho Cass are so scarce that fewer than 20 are known in the entire Milky Way. What makes them unique? They occupy a precarious middle ground in stellar evolution, too massive to burn quietly like the sun, yet not quite unstable enough to become full-fledged red supergiants. They're the universe's way of showing us that even stars can have identity crises. Perched in the iconic W-shaped constellation Cassiopeia, Rho Cass seems unassuming at first glance. But beneath that golden glow lies a history of violence. In 2001, astronomers watched in awe as the star ejected an entire solar mass worth of material, enough gas to form a whole new star in a single eruption. The event wasn't just dramatic, it was a cosmic gut punch. For months, Rho Cass dimmed dramatically, its outer layers cooling into dust as they expanded into space. Then, like a phoenix, it reignited, returning to its former brilliance as if nothing had happened. These outbursts aren't flukes, they're part of Rho Cass's volatile personality, a symptom of its struggle to balance gravity's pull against the radiation pressure trying to tear it apart. What's truly fascinating about Rho-Cas is how it teeters on the edge of destruction. Yellow hypergiants exist in a transitional phase, caught between burning hydrogen in their cores and the looming threat of collapse. For Rho-Cas, this means an almost schizophrenic existence, one moment a radiant beacon, the next a convulsing furnace on the verge of self-immolation. Its surface temperature swings wildly, oscillating between 7,000 and 4,000 Kelvin, as if the star can't decide whether to be a yellow giant or a red supergiant. And then there's its home. Cassiopeia isn't just a pretty asterism, it's a celestial crossroads rich with star-forming regions and supernova remnants. Rho-Cas sits near the midpoint of the W, a golden sentinel watching over a realm of stellar birth and death. Its eruptions don't just vanish into the void, they enrich the surrounding space with heavy elements, contributing to the chemical stew that might one day form new stars and planets. But Rho-Cas's days are numbered. In astronomical terms, it's already on borrowed time. Within the next few 100,000 years, it will likely shed even more mass before finally collapsing in a supernova. When that happens, the explosion will be visible from Earth, a fleeting but brilliant addition to Cassiopeia's storied legacy. Until then, Rho-Cas remains a cosmic paradox, a star that's both dazzling and doomed, teaching us that even the rarest celestial objects are part of the universe's relentless cycle of creation and destruction. Zeta Puppis, also known as NOWs, isn't just hurtling through space, it's making a grand escape. Clocking in at 60 kilometers per second, this blue supergiant moves so fast, it doesn't merely travel through the interstellar medium, it bulldozes it, carving a colossal bow shock in its wake like a ship plowing through cosmic waters. This shockwave, visible in ultraviolet and X-ray light, is a telltale sign of a star that's not just living life in the fast lane, it's rewriting the rules of stellar motion. But speed isn't NOWs' only claim to fame. This star is a fugitive, a runaway kicked out of its home by cosmic violence. Most massive stars like this are born in dense clusters surrounded by siblings. NOWs, however, travels alone, and its trajectory tells a story of celestial betrayal. Astronomers believe it was once part of a binary system, locked in orbit with another massive star. When that companion exploded as a supernova, the sudden loss of gravitational tether sent NOWs careening into space like a slingshot released at full force. The energy of that explosion didn't just expel the star, it sent it racing across the galaxy with enough momentum to escape the gravitational pull of its birthplace forever. What's astonishing is how this history is etched into the star itself. NOWs spins at a breakneck pace, rotating so fast its equator bulges outward. This rapid spin is another clue to its violent past, likely a consequence of absorbing angular momentum from its doomed companion before the supernova. Now it's a stellar solo act, burning with a brilliance 50,000 times that of the Sun. Its intense ultraviolet radiation peeling away layers of nearby gas, sculpting the surrounding nebula into eerie, glowing shapes. Yet NOWs' journey isn't just about destruction. As it barrels through space, it seeds the interstellar medium with heavy elements, churned up from its core and blasted outward by its ferocious stellar winds. These elements, forged in the star's nuclear furnace, will one day become part of new stars, planets, and perhaps even life. In a way, NOWs isn't just running, it's sowing the very ingredients of future cosmic wonders. For astronomers, this runaway star is a gold mine. Its trajectory offers a rare glimpse into the chaotic dynamics of binary systems and the explosive forces that can send stars hurtling across the galaxy. And its bow shock serves as a natural laboratory, revealing how massive stars interact with the thin gas between the stars. NOWs reminds us that the universe isn't static. It's a place of motion, upheaval, and second chances, where even a star cast adrift can blaze a trail that lights up the cosmos. At the heart of the Orion Nebula, where newborn stars flicker like diamonds scattered across velvet, one stellar titan reigns supreme, the one Orionis C. This isn't just another bright spot in the trapezium cluster, it's the cosmic engine powering the entire nebula's glow. With a surface temperature soaring above 40,000 Kelvin, the one Orionis C pumps out ultraviolet radiation so intense it strips electrons from hydrogen atoms in a process called ionization. The result, that ethereal glow we see in telescope images the nebula's gas fluorescing like a celestial neon sign, energized by this single star's relentless output. But radiation isn't its only weapon. Theta 1 Orionis C unleashes stellar winds moving at thousands of kilometers per second, gusts so powerful they sculpt the surrounding gas into towering pillars and cavernous voids. These winds don't just shape the nebula's beauty, they're midwives for star formation. By compressing nearby gas clouds, they trigger gravitational collapses that birth new stars, making this hypergiant both a creator and a destroyer. The Orion Nebula's famous protoplanetary disks, where infant planets coalesce, owe their very existence to this delicate dance of chaos and creation. What's truly remarkable is how recently we've grasped its dominance. For centuries, astronomers saw the trapezium stars as a collective light source. Only in the 1990s did high-resolution observations reveal the one Orionis C's outsized role. Its luminosity, 250,000 times that of our Sun, accounts for nearly 90% of the ionizing radiation flooding the nebula. Without it, Orion's iconic glow would fade into near darkness like a city skyline deprived of electricity. Yet this star's influence stretches beyond mere illumination. Its ultraviolet radiation heats surrounding dust, altering the chemistry of nascent planetary systems. Its winds clear away debris, giving younger stars room to breathe. And its very presence serves as a laboratory for understanding how massive stars dictate the evolution of their stellar nurseries. Theta 1 Orionis C is more than a star. It's a galactic architect, proving that sometimes the universe's most breathtaking beauty begins with a single, searing point of light. P Cygni isn't just a star, it's a living relic of cosmic history. Back in the summer of 1600, astronomers across Europe gasped as a new point of light flared to life in the constellation Cygnus. This wasn't some distant supernova, it was a previously invisible star suddenly blazing into view, bright enough to rival the stars of the Big Dipper. For 6 years, it flickered like a candle in the wind before fading from naked eye visibility. But P Cygni wasn't done. Over the centuries, it's erupted multiple times, earning its place as one of the first documented variable stars, a celestial rebel that refuses to follow the rules. Today, we know this cosmic enigma as a luminous blue variable, a hypergiant so unstable, it's essentially a star wearing a disguise. From Earth, it looks deceptively ordinary, a steady blue pinpoint. But zoom in and the truth unravels. P Cygni's spectrum reveals a telltale signature, emission lines paired with absorption troughs, a pattern so distinctive, astronomers now call similar features P Cygni profiles in stars across the universe. These spectral fingerprints betray a star hemorrhaging material at breakneck speeds. Imagine a hurricane where the winds don't blow at hundreds of miles per hour but at thousands, stripping away the star's own atmosphere and flinging it into space. That's P Cygni's daily reality. What makes this star truly remarkable is its balancing act. Most hypergiants this massive, 50 times heavier than our Sun, don't last long. They burn through their fuel in a few million years before exploding in spectacular supernova. P Cygni, though, has clung to existence for centuries, teetering between eruption and stability. Its surface simmers at 18,000 Kelvin, hot enough to vaporize steel, while its winds blast outward at nearly 700 kilometers per second. Yet somehow it persists, puffing away layers like a cosmic onion peeling itself. The secret might lie in its eruptions. Every few decades, P Cygni undergoes violent outbursts, ejecting massive shells of gas that temporarily shroud its brilliance. These aren't random tantrums, they're pressure releases, the star's way of preventing total collapse. By shedding mass in controlled bursts, it buys itself more time, staving off the inevitable explosion that will one day end its turbulent life. For astronomers, P Cygni is a Rosetta Stone. Its historic eruptions taught us that stars aren't static. They evolve, convulse, and sometimes reinvent themselves overnight. Its spectral lines reveal the violent choreography of stellar winds, helping us decode the lives of distant hypergiants, and its very existence challenges our models, proving that even the universe's most extreme stars can find ways to endure, at least for a while. In a cosmos full of fleeting wonders, P Cygni stands as a reminder that some stars don't just shine, they fight. HD 93129A isn't just a star. It's a celestial power couple, a binary supergiant so intense it rewrites the chemistry of its cosmic neighborhood. Nestled in the turbulent Carina Nebula, this duo consists of two massive stars locked in a gravitational dance, with the primary star stealing the spotlight as one of the most luminous objects in the Milky Way. If the Sun were a candle, HD 93129A's primary would be a supercharged lighthouse beam, blasting out ultraviolet radiation at levels so extreme it tears electrons from atoms light years away. What makes this system truly remarkable is how it dominates its surroundings. The Carina Nebula is already a stellar nursery teeming with young, hot stars, but HD 93129A's primary outshines them all. Its ultraviolet output is so fierce it ionizes vast swaths of hydrogen gas, creating a glowing bubble of plasma around the binary pair. This isn't just a pretty light show, it's a cosmic chemistry lab. By stripping electrons from atoms, the star fundamentally alters the nebula's composition, breaking apart molecules and forging new ones in the chaos. Elements that would normally remain locked in dust grains get liberated, floating freely in the energized gas. But here's where the binary nature of this system kicks things up a notch. The gravitational tug of war between the two stars stirs the surrounding nebula like a spoon in a cauldron, churning the gas and dust into turbulent waves. This motion does more than create stunning Hubble images, it triggers pockets of star formation. Dense regions of gas, compressed by the star's radiation and gravitational tides, collapse under their own weight, igniting new stars in their wake. In a way, HD 93129A isn't just shaping the Carina Nebula, it's parenting the next generation of stellar giants. The chemistry here is unlike anything in quieter regions of space. Normally, complex molecules like water or carbon monoxide form in the shielded depths of cold gas clouds. But in HD 93129A's realm, these molecules get shredded by ultraviolet radiation, only to reform in the turbulent eddies between the stars. It's a cycle of destruction and creation playing out on a cosmic scale, proving that even the harshest environments can brew the ingredients for life. When this binary eventually meets its end, likely in a pair of supernova, the shockwaves will ripple through the Carina Nebula, scattering heavy elements like oxygen, silicon, and iron into the void. These elements, forged in the star's cores, will one day become part of new planets, oceans, or even living organisms. HD 93129A isn't just a spectacle. It's a reminder that the universe's most violent actors are also its most creative architects. AG Carinae doesn't just shine, it sculpts. This luminous blue variable, nestled in the southern constellation Carina, is an artist whose medium is cosmic chaos. Over the past 10,000 years, its violent eruptions have chiseled intricate nebulous structures from the surrounding gas, creating a celestial masterpiece visible across thousands of light years. The star's most famous artwork, the Homunculus Nebula's lesser-known cousin, a sprawling, bubble-like shell of ejected material, glowing in hues of blue and red as it expands into the void. Each filament and knot in this nebula tells a story, a tantrum from A.G. Carroney's turbulent past frozen in time. Right now, the star is in a precarious balancing act. Like a tightrope walker swaying over an abyss, A.G. Carroney teeters between stability and self-destruction. Its surface temperature swings wildly, sometimes blazing at 20,000 Kelvin, other times cooling to 8,000, as it struggles to contain the nuclear fires raging in its core. The star's outer layers are barely hanging on, held together by gravity's weakening grip. Stellar winds scream outward at speeds topping 7 million kilometers per hour, stripping away mass equivalent to an entire Earth every year. This isn't just shedding, it's stellar hemorrhage. Astronomers monitor A.G. Carroney like a ticking time bomb because in many ways it is. Luminous blue variables are notorious for their explosive demises, and this one checks all the boxes for an impending catastrophe. Extreme mass loss, erratic brightness fluctuations, and a core burning through its fuel at a breakneck pace. The star's current eruptions might seem dramatic, but they're likely just preludes to the main event, a supernova or even a hypernova capable of outshining its entire host galaxy. What makes A.G. Carroney truly mesmerizing is how its violence births beauty. The very eruptions that threaten its existence also enrich the cosmos. Each outburst seeds the surrounding nebula with heavy elements: carbon, nitrogen, oxygen forged in its nuclear furnace. These elements will one day become building blocks for new stars, planets, and perhaps even life. In that sense, A.G. Carroney's tantrums aren't just destruction, they're a vital part of the universe's recycling program, where the death throes of one star become the raw materials for another's birth. For now, it remains one of the Milky Way's most captivating enigmas, a star that's both creator and destroyer, whose outbursts paint the cosmos even as they herald its own doom. Every flicker in its brightness, every fresh plume of ejected gas, is a clue, a whisper of the apocalyptic finale yet to come. And when that finale arrives, it won't just be an ending. It'll be a spectacle that reshapes its corner of the galaxy forever. WR-142 isn't just another Wolf-Rayet star, it's a cosmic alchemist caught mid-transformation, forging elements deep in its core that most stars can only dream of producing. With a surface temperature scorching at 200,000 Kelvin, this stellar furnace is so blisteringly hot, it makes blue supergiants seem lukewarm by comparison. But what truly sets it apart isn't just the heat, it's what's billowing off its surface. Unlike typical stars shrouded in hydrogen or helium, WR-142's winds are laced with something far rarer: oxygen. So much oxygen, in fact, that astronomers classify it as part of an exclusive club oxygen sequence, Wolf-Rayet, a fleeting phase in the life of the universe's most massive stars. This oxygen-rich atmosphere isn't just a curiosity, it's a time capsule. WR-142 is essentially wearing its nuclear fusion history on its sleeve. Deep in its core, where temperatures exceed 1 billion degrees, helium atoms have been crushed together to form carbon, then fused again to create oxygen. In most stars, these elements would remain trapped beneath layers of unburnt fuel. But WR-142 has stripped itself bare, shedding its outer hydrogen and helium envelopes through ferocious stellar winds, exposing the elemental forge within. What we're seeing is the star's own skeleton, a chemical fingerprint of its violent evolution. The process unfolding here is called nucleosynthesis, and WR-142 is a masterclass in how stars build the universe's periodic table. Every carbon atom in your body, every oxygen molecule you breathe, they were all cooked in stars like this one. But while most stars release these elements slowly, Wolf-Rayets are cosmic pressure cookers, expelling their heavy element bounty at hypersonic speeds. WR-142's winds scream outward at over 5,000 kilometers per second, spraying nearby space with oxygen that will one day seed new stars, planets, and perhaps even life. Yet this phase is tragically short-lived. Oxygen sequence Wolf-Rayets are the dying breaths of stellar giants, a final defiant blaze before collapse. Within the next few 100,000 years, a blink in cosmic time, WR-142's core will exhaust its fuel, triggering a supernova so powerful it'll outshine galaxies. The explosion won't just be a spectacle, it'll scatter its oxygen-rich guts across the cosmos, further enriching the interstellar medium. In a way, WR-142 isn't just a star. It's a bridge between stellar life and death, a reminder that even in destruction, the universe is always building. IRC plus 10,420 isn't just a star. It's a cosmic metamorphosis in progress, caught mid-leap between two stellar identities. Most of the universe's giants stay in one phase for millions of years, but this hypergiant is rewriting its destiny at breakneck speed, transitioning from a yellow hypergiant to a Wolf-Rayet in what amounts to a celestial blink of an eye. Nestled 20,000 light-years away in the constellation Aquila, IRC plus 10,420 is racing through its evolution so fast, astronomers can practically watch it happen. What makes this star impossible to ignore isn't just its transformation, it's the spectacular way it announces itself. Shrouded in a thick cocoon of its own making, IRC plus 10,420 pumps out so much infrared radiation, it's one of the brightest objects in the sky at those wavelengths. That glow comes from dust, countless grains ejected during violent outbursts, now floating around the star like a luminous fog. But here's the twist, this isn't just any dust. It's stardust in the truest sense, forged from the star's own shredded outer layers, rich with heavy elements like oxygen, silicon, and carbon. Every particle is a tiny tombstone, marking material IRC plus 10,420 can no longer hold onto. Peering through that veil reveals a star in turmoil. Spectral lines show atmospheric speeds exceeding 700 kilometers per second, winds so fast they could circle Earth in under a minute. These aren't gentle breezes, they're hurricane-force ejections, stripping the star down to its bare essentials. That's the hallmark of a Wolf-Rayet in the making, a star so eager to shed its skin, it's practically unraveling. Yet IRC plus 10,420 still clings to traces of its yellow hypergiant past. Its surface temperature swings between 8,000 and 12,000 Kelvin, as if it can't decide whether to cool into a red supergiant or heat up into a blue Wolf-Rayet. The most startling clue to its identity crisis lies in its surroundings. Most hypergiants create symmetrical nebulae, but IRC plus 10,420 ejecta form chaotic, knotted structures, like a series of explosions frozen in time. Hubble images reveal concentric shells of material relics of past eruptions now being plowed through by newer, faster winds. It's as if the star is vomiting its guts out in waves, each more violent than the last. This isn't orderly shedding, it's stellar desperation. Why the rush? The answer might lie in IRC plus 10,420 mass, tipping the scales at over 40 times the sun's weight. It's too big to age gracefully. Stars this massive live fast die young and often skip evolutionary steps altogether. Some theorists suggest it might have already been a red supergiant before reheating, an ultra-rare blue loop event, while others argue it's racing toward a Wolf-Rayet phase to stabilize before total collapse. Either way, its fate is sealed. Within the next few thousand years, IRC plus 10,420 will likely explode as a supernova, scattering those dust-rich ejecta across the galaxy. For now, this transitioning titan offers a front-row seat to stellar evolution's most dramatic acts. It's proof that even stars don't get to stand still, and that sometimes the most breathtaking cosmic sights come from the chaos of reinvention. V838 Monocerotes didn't just erupt in 2002, it staged a cosmic magic trick that left astronomers speechless. Overnight, This unassuming star in the constellation Monoceros flared to over 600,000 times its original brightness, temporarily outshining the entire Milky Way. But unlike typical stellar explosions that fade within weeks, V838 Mon's outburst had an encore, eerie, expanding halos of light that rippled outward for years, illuminating interstellar dust like a flashlight beam sweeping across a smoky room. These light echoes became one of Hubble's most iconic images, a series of shimmering concentric rings that made it seem as though the star was trapped inside a giant, glowing onion. The cause of this celestial light show remains one of modern astronomy's greatest puzzles. Most stellar eruptions follow predictable patterns. Supernova blow stars apart, nova eject surface material, and luminous blue variables shed their outer layers. V838 Mon fit none of these molds. Its temperature plummeted as it brightened the opposite of what physics predicts, and the expanding light echoes moved far too slowly to match any known explosion speed. The leading theory suggests a stellar merger, where V838 Mon devoured a smaller companion star in a fit of cosmic cannibalism. The ingested star's energy would have triggered runaway fusion in the primary star's core, leading to that bizarre cooling, brightening effect. Others propose it was a born-again red giant, reigniting long-dormant nuclear reactions in its core in a last-ditch effort to stave off collapse. What makes V838 Mon truly revolutionary is how it redefined our understanding of stellar death throes. Before this event, astronomers had no idea stars could produce such prolonged light echoes. The phenomenon occurs when light from the initial explosion travels outward at, well, light speed, while simultaneously illuminating shells of dust at varying distances. The result, a delayed light show where the same flash appears to move outward over years as it reaches progressively more distant dust layers. These echoes became a new tool for mapping interstellar dust in 3 dimensions, a celestial sonar using light instead of sound. The echoes also revealed something startling about the star's environment. Their intricate patterns showed the dust around V838 Mon wasn't evenly distributed but sculpted into delicate filaments and tendrils, likely shaped by ancient stellar winds. Some rings appeared broken or warped, betraying the presence of magnetic fields twisting the dust on microscopic scales. For the first time, astronomers could study the fine structure of interstellar dust hundreds of light years away with unprecedented clarity, all thanks to one star's mysterious tantrum. 2 decades later, V838 Mon has dimmed to near obscurity, but its legacy endures. The event challenged textbook models of stellar evolution, proving that stars can explode without destroying themselves, at least temporarily. It gave us a new way to probe the galaxy's hidden architecture, and perhaps most importantly, it reminded us that for all our advanced telescopes and supercomputers, the universe still holds surprises that defy our best theories. V838 Mon's light may have faded, but the questions it ignited continue burning bright in the minds of astronomers worldwide. Sure 25 doesn't just burn, it lies. This blue supergiant, tucked inside the brilliant stellar factory of NGC 3603, pulled off one of the most convincing acts of cosmic deception in modern astronomy. For years, researchers watched as it flared with the intensity of an impending supernova, ejecting shells of material in violent outbursts that mirrored the final death throes of massive stars. The show was so convincing, many braced for the inevitable explosion until the star did something unexpected. It survived, no supernova, no collapse. Just a star that flirted with destruction and walked away, leaving behind an eerie hourglass nebula as the only evidence of its near-death experience. What makes this stellar trickster so fascinating is the aftermath of its false alarm. Most dying stars shed their outer layers in messy, asymmetrical clouds, but Sure 25 sculpted something far more precise, a near-perfect hourglass of ejected gas, pinched at the waist like an interstellar timepiece. This structure isn't just pretty, it's a forensic snapshot of the star's tantrum. The hourglass shape suggests SHER 25 didn't erupt uniformly. Instead, material blasted outward along polar jets, funneled by magnetic fields or the star's own rapid rotation, while equatorial winds remained weaker. The result, a nebula that looks less like an explosion and more like a piece of cosmic blown glass. But here's the real puzzle. Why did SHER 25 stage this performance at all? Most blue supergiants don't behave this way. They either explode or fade quietly. One theory points to a hidden companion, a smaller star whose gravitational tugs might have destabilized SHER 25's outer layers, triggering the eruption. Another possibility involves internal upheaval, a sudden reshuffling of nuclear reactions in the star's core that sent shockwaves rippling outward. Whatever the cause, the event left behind more than just a nebula. It left clues. The chemical composition of that hourglass is laced with nitrogen-enriched material, a telltale sign of deep dredge up the process by which fusion byproducts from the star's core get hauled to the surface during violent convulsions. For astronomers, SHER 25 is a goldmine precisely because it didn't die. Most supernova studies rely on after-the-fact forensics, piecing together a star's final moments from the debris it leaves behind. Here we have a rare case of a star caught mid-crisis, offering a preview of the processes that precede an actual explosion. That hourglass nebula isn't just debris, it's a training ground. By studying its structure and chemistry, researchers can refine models of how massive stars shed mass before their final detonation, helping predict what signatures to look for in real-time supernova observations. SHER 25's story isn't over. It's still unstable, still capable of surprises. One day, it might yet fulfill its earlier promise and go supernova for real. Until then, it stands as a cosmic lesson in humility, a reminder that even the universe's most predictable-seeming processes can still keep secrets. And when the next star erupts, astronomers will be watching, wondering, is this the real thing or just another stellar impersonator playing pretend with the forces of destruction? HV 2112 isn't just a star. It's a cosmic Russian nesting doll with a potentially mind-bending secret. Lurking in the small Magellanic Cloud, this luminous variable star has astronomers locked in debate over whether it's the first confirmed example of a Thorne-Zitkow object, a theoretical stellar hybrid where a red supergiant swallows a neutron star whole. Picture this, deep within the star's churning plasma, where temperatures reach millions of degrees, there could be an entire neutron star orbiting silently, its immense density warping the surrounding nuclear reactions like a lead weight in a bowl of gelatin. The theory behind these bizarre objects reads like astrophysical fan fiction. When a massive star in a binary system explodes as a supernova, its collapsed core, now a neutron star, can get kicked into an orbit that spirals straight into its companion star. Instead of being destroyed, the neutron star plunges through the outer layers and comes to rest at the heart of its neighbor, turning the star into a cosmic Matryoshka doll. The neutron star's ridiculous density, a teaspoon of its material would weigh billions of tons, completely alters how the host star burns its fuel. Normal stars fuse hydrogen in their cores, but a Thorne-Zitkow object's core is essentially hijacked, with nuclear reactions occurring in a swirling plasma around the neutron star instead. What makes HV 2112 such a compelling candidate are the chemical fingerprints in its light. The star's spectrum shows bizarrely high amounts of rubidium, lithium, and molybdenum elements that form in exactly the extreme conditions a neutron star core would create. In a normal red supergiant, these elements should be virtually absent. It's like finding a jet engine inside a horse-drawn carriage. The parts simply don't belong unless something extraordinary is happening under the hood. But not everyone's convinced. Some researchers argue HV 2112 chemistry could come from a recent merger with another star, or that we're misinterpreting the spectral lines altogether. The debate hinges on a critical question: can a neutron star actually survive being swallowed without shredding its host star apart? Simulations show it's possible, if the infall happens just right, but the odds seem astronomical. Yet if Thorne-Zitkow objects do exist, they'd rewrite chapters of stellar physics, proving stars can evolve in ways we never imagined possible. For now, HV 2112 remains an enigma, a stellar oddball that might be hiding the universe's most extreme stellar hybrid, or might just be an unusually fussy red supergiant. Either way, its very existence pushes us to rethink what stars are capable of. And if future observations confirm the neutron star at its heart, it would mean the universe has been crafting these cosmic matryoshkas all along, hiding neutron stars in plain sight inside what look like ordinary giant stars. Sometimes the most extraordinary discoveries aren't new objects, they're new ways of seeing what's been there all along. CXOJ 164710 455,216 isn't your average neutron star. It's a cosmic bullet wrapped in the universe's most powerful magnetic field. Dubbed a magnetar, this stellar remnant doesn't just possess a magnetic field, it wields one so intense it bends the rules of physics. At 10 to the 15th Gauss, its magnetism is a quadrillion times stronger than Earth. To put that into perspective, if this magnetar were halfway to the moon, its magnetic pull would erase the data on every credit card on our planet. But what makes CXOJ 164710 455,216 truly extraordinary isn't just its magnetism, it's the fact that it's racing through space at over 2 million miles per hour, leaving a trail of questions in its wake. This cosmic speedster didn't start its journey alone. Astronomers trace its origins back to Westerlund 1, a dense, glittering star cluster about 12,000 light-years away. Clusters like this are stellar nurseries for massive stars, but they're also cosmic demolition derbies, places where gravitational tussles can fling stars into the void at unimaginable speeds. The prevailing theory suggests CXOJ 164710 455,216 was once part of a binary pair. When its companion star exploded as a supernova, the asymmetric detonation acted like a slingshot, hurling the magnetar outward while the shockwave amplified its magnetic field to ludicrous extremes. The result, a stellar remnant so powerful, it can crack its own crust, triggering starquakes that ripple across space as gamma-ray flares bright enough to outshine the entire Milky Way for a fraction of a second. What's even wilder is how this magnetar defies expectations. Most neutron stars spin rapidly at birth, slowing over time as their magnetic fields sap energy. But CXOJ 164710 455,216 bucks the trend. Despite being millions of years old, it still rotates once every 10 seconds, a glacial pace for neutron stars, yet its magnetic field hasn't faded. This paradox suggests something unusual is at work, possibly a dynamo effect deep in its core, where quantum mechanics and extreme gravity conspire to keep the magnetic engine running. The star's violent past isn't just theoretical. Westerlund 1 is littered with the corpses of massive stars, including another magnetar and multiple black holes, making it a graveyard of stellar giants. For CXOJ 164710 455,216 to escape this chaos required perfect conditions. A supernova explosion precise enough to eject it without obliterating it entirely. That it survived at all is a testament to the universe's ability to forge wonders in the crucible of destruction. Today, this runaway magnetar serves as a natural laboratory for studying the limits of magnetic fields and the aftermath of stellar cataclysms. Its very existence pushes the boundaries of what we thought possible, proving that even in death, stars can become more extreme than anything we've witnessed in life. And as it streaks across the galaxy, it carries with it the untold story of Westerland, one most dramatic escape, a relic of cosmic violence still echoing across the ages. SDSS J102,915 plus 172927 isn't just old, it's a living fossil, a time capsule from an era when the universe itself was in its infancy. Nestled in the constellation Leo, this unassuming star holds a record that's almost incomprehensible. It contains 200,000 times less metal than our Sun. That's not just a small difference, it's like comparing a single grain of sand to an entire desert. For astronomers, this makes J102,915 a Rosetta Stone, offering clues about what the cosmos looked like over 13 billion years ago when the first stars flickered to life in the darkness of the early universe. What makes this star so revolutionary isn't just its age, it's the way it defies expectations. Current theories suggest the very first stars, known as Population 3, should have been unimaginably massive, hundreds of times heavier than our Sun, burning fiercely and dying young in colossal supernova. These explosions would have seeded the cosmos with heavier elements, paving the way for smaller, metal-rich stars like those we see today. But J102,915 doesn't fit that narrative. It's tiny, just 0.8 times the mass of the Sun, and yet its composition suggests it formed from nearly pristine gas, untouched by those early supernova. Somehow, this star exists in a form theory claimed shouldn't be possible, a relic from a time before metals polluted the stellar nursery. The implications are staggering. If stars like J102,915 could form without relying on the debris of earlier giants, it means the early universe might have been far more diverse than we imagined. Perhaps not all primordial gas collapsed into supermassive stars. Maybe some quietly condensed into smaller, longer-lived objects, hiding in plain sight until now. This would rewrite the opening chapters of cosmic history, suggesting pockets of the infant universe could have skipped the era of titanic stars entirely. Then there's the mystery of its longevity. With so few heavy elements which normally help stars cool and collapse, how did this star form at all? One radical theory proposes that dark matter might have played a role, its gravitational influence providing just enough compression to ignite nuclear fusion without the usual metallic catalysts. Others suggest that in the ultra-dense early universe, even pristine hydrogen could have fragmented directly into small stars under the right conditions. Yet the most tantalizing possibility is that J102,915 isn't alone. If one such star exists, there might be others older, quieter, and even more metal-poor, lurking in the galactic outskirts. Each one could be a missing link, a piece of the puzzle showing how the universe transitioned from simplicity to complexity. For now, this ancient survivor stands as both a challenge and an invitation, reminding us that the cosmos always has more secrets to reveal. KIC 8462852, better known as Tabby's star, doesn't just flicker, it vanishes. Imagine a star that occasionally dims by up to 22%, as if something colossal is passing in front of it, blotting out its light in irregular, unpredictable dips. This isn't the gentle fade of a planet transiting or the rhythmic pulse of a variable star. It's erratic, dramatic, and utterly perplexing. When astronomer Tabby first documented its bizarre behavior in 2015, the discovery sent shockwaves through the scientific community. Here was a star defying every conventional explanation, a cosmic enigma that sparked debates ranging from mundane astrophysics to the tantalizing possibility of alien megastructures. The most startling aspect of Tabby's star isn't just the depth of the dimming, it's the pattern. Most stars with transiting objects show symmetrical, periodic dips as planets or dust clouds pass by. But Tabby's star's light curves look chaotic, with some drops lasting days, others weeks, and no discernible rhythm. Early observations ruled out planets, even a Jupiter-sized world would only block about 1% of the star's light, not 22%. Comets were the next suspect, but the sheer scale required swarms of thousands of giant comets, stretches plausibility. Dust clouds could explain some dimming, yet they'd also scatter infrared light, which Tabby's star doesn't exhibit in the expected amounts. Every hypothesis seems to hit a wall, leaving astronomers scrambling for answers. Then came the wildcard theory, alien megastructures, specifically a Dyson swarm, a hypothetical array of energy collecting satellites or panels built by an advanced civilization to harness their star's power. The idea, first proposed by physicist Freeman Dyson in the 1960s, found new life with Tabby's star's erratic behavior. Could these dimming events be the shadows of vast construction projects eclipsing the star? The notion electrified the public imagination, but scientists remained cautious. Extraordinary claims require extraordinary evidence, and no one could rule out natural explanations. Still, the possibility lingered, making Tabby's star a rare case where astronomy and science fiction briefly overlapped. Further observations only deepened the mystery. In 2017, the star dimmed again, but this time astronomers caught it in action. Spectroscopic data revealed that the dimming was wavelength-dependent blue light dimmed more than red, a smoking gun for fine dust particles. This pointed toward natural causes, like a circumstellar debris disk or a shattered exomoon's remnants. Yet even this explanation feels incomplete. The dust would need to orbit in a bizarrely clumpy, uneven distribution to account for the star's most extreme dips. And why is the star also slowly, steadily fading over decades? None of the pieces quite fit. Tabby's star remains one of astronomy's most compelling open cases, a reminder that the universe constantly defies our expectations. Whether the answer is mundane or unimaginable, this star has already reshaped how we search for anomalies in the cosmos. Future telescopes like the James Webb or the upcoming Vera Rubin Observatory may finally crack the puzzle. Until then, Tabby's star stands as a beacon of curiosity, challenging us to look deeper and question everything we think we know about the stars. S50014+81 isn't just a black hole, it's a cosmic supernova on permanent overdrive. Technically classified as a quasar, this ultramassive monster sits at the heart of a distant galaxy, devouring matter with such ferocity that its accretion disk blazes with the luminosity of 10 trillion suns. To put that into perspective, if this thing replaced our sun, its light wouldn't just outshine every star in the Milky Way, it would vaporize our solar system within seconds. Yet what makes S50014+81 truly terrifying isn't just its brightness. It's the sheer scale of the engine behind it, a black hole weighing in at 40 billion solar masses, so vast it could swallow our entire local group of galaxies without breaking a gravitational sweat. How does something this colossal even form? The answer lies in the universe's most gluttonous growth spurt. Most supermassive black holes start small, stellar remnants that grow by slowly merging with others or accreting gas over billions of years. But S50014+81 skipped the appetizer course. It likely formed during the cosmic dawn, when the universe was awash with pristine gas clouds so dense they collapsed directly into black holes thousands of times the sun's mass. These primordial seeds then gorged themselves on the surrounding chaos, merging with rivals and gulping down galaxies whole during an era when the cosmos was tighter. Collisions were frequent and the rules of physics ran wild. The result is a gravitational titan that defies logic. Its event horizon stretches farther than Neptune's orbit, a boundary so vast that time itself slows to a crawl near its edge. Matter circling the drain doesn't just heat up, it gets shredded into plasma, spinning at near light speed and generating magnetic fields strong enough to twist space like taffy. The energy released in this maelstrom doesn't just glow, it punches through the universe as jets of radiation so powerful they can be detected halfway across the observable cosmos. And here's the kicker. We're seeing S50014 plus 81 as it was 12.7 billion years ago, meaning this beast reached its staggering size when the universe was barely 1 billion years old. That's like finding a skyscraper in the Stone Age. It shouldn't be possible, yet there it is. Yet for all its fury, S50014 plus 81 is also a cosmic sculptor. The radiation from its accretion disk ionizes gas across entire galaxy clusters, suppressing star formation in some regions while triggering it in others. Its jets carve cavities in intergalactic space, creating bubbles of million-degree gas that persist for eons. Even in destruction, this quasar shapes the universe, proof that the cosmos's most violent forces are also its most creative. The only question left is what other monsters like it are lurking in the darkness, waiting to be discovered. Swift J1644 plus 57 isn't just a cosmic flare, it's the aftermath of a star's final, fatal tango with a black hole. Back in 2011, telescopes caught this event unfolding in a distant galaxy, 3.8 billion light-years away. At its peak, the outburst blazed with the brightness of 100 billion suns, outshining every star in its host galaxy combined. But this wasn't just another supernova or quasar. It was something far rarer, a tidal disruption event, the moment a wandering star ventured too close to a sleeping black hole and paid the ultimate price. The physics behind this cataclysm is both brutal and beautiful. As the star crossed the black hole's event horizon, gravitational forces stretched it like taffy, a process called spaghettification. The side nearest the black hole experienced exponentially stronger gravity than the far side, tearing the star apart in a matter of hours. But the real spectacle began when the debris formed a swirling accretion disk, superheating to millions of degrees and launching jets of plasma at nearly light speed. These jets, aligned almost perfectly with Earth's line of sight, acted like cosmic blowtorches, amplifying the event's visibility across the universe. What we witnessed wasn't just a star's death. It was the black hole's awakening feast, broadcast in X-rays and gamma rays brighter than anything seen before. Events like Swift J1644 plus 57 are more than just fireworks. They're laboratories for extreme physics. The jets alone defy conventional models, packing enough energy to challenge our understanding of how black holes channel matter. Normally, black holes are messy eaters, swallowing most material without fanfare. But here, the black hole, a relatively lightweight at 1 million solar masses, somehow converted stellar debris into focused beams with staggering efficiency. That unexpected precision hints at hidden magnetic mechanisms or spin dynamics we're only beginning to grasp. Even the aftermath holds secrets. Tidal disruptions leave behind chemical footprints, heavy elements forged in the star's final moments and scattered by the explosion. These elements, like iron and nickel, become cosmic breadcrumbs, tracing how black holes redistribute matter through galaxies. And because these events flare so brightly, they serve as beacons for studying otherwise invisible black holes lurking in quiet galaxies. Swift J1644 plus 57 reminds us that destruction in space isn't just an end, it's a transformation. A star's obliteration becomes a black hole's revelation, lighting up the darkness with answers to questions we're still learning to ask. Before the galaxies, before the planets, before even the atoms that make up our bodies, there was a generation of stars so alien, so unimaginably powerful, they made today's supergiants look like flickering candles. These were the population 3 stars, the universe's first attempt at turning primordial chaos into light. Born in the absolute darkness of the cosmic dawn, these titans were nothing like the stars we know today. With masses ranging from 100 to 1,000 times that of our Sun, they burned at temperatures exceeding 100,000 Kelvin, their surfaces bathed in the raw ultraviolet fury of pure hydrogen and helium fusion. Picture a star so massive, its core pressure didn't just fuse hydrogen into helium, it forged heavier elements in a single, violent lifetime that lasted barely a few million years. These weren't just stars, they were cosmic alchemy furnaces running at full blast from birth to death, and when they died, they did so spectacularly. Unlike modern supernova, which leave behind neutron stars or black holes, these behemoths likely underwent pair instability explosions, cataclysmic detonations so powerful, they vaporized the entire star, leaving no remnant behind. The energy released in these blasts would have outshone entire galaxies, flooding the early universe with enough radiation to reionize vast swaths of neutral hydrogen and kick-start the epoch of light we still live in today. But their real legacy lies in the elements they forged. Every atom of oxygen in your lungs, every speck of carbon in your DNA, every fleck of gold in a wedding ring, they all trace their origins back to these primordial giants. Population 3 stars were the universe's first factories for heavy elements, synthesizing them in their cores and scattering them across the cosmos in their explosive deaths. The catch: they were so efficient at this process, they effectively poisoned the well for future stars. The metals they ejected into space altered the chemistry of later stellar nurseries, making it impossible for stars this massive to form ever again. It's why we'll never see their like in the modern universe. They literally changed the rules of star formation forever. The hunt for evidence of these ancient leviathans continues. While none survive today, astronomers search for their chemical fingerprints in the atmospheres of the universe's oldest stars, like SDSS-J 102,915 plus 172927. Some even speculate that the supermassive black holes anchoring today's galaxies might be the corpses of especially massive population 3 stars, collapsed directly into black holes without the usual supernova fanfare. What's certain is that these pioneers didn't just light up the cosmos, they built the very periodic table we take for granted. In a very real sense, we are all stardust, but some of us are more ancient stardust than others. From hypergiants so vast they could swallow our solar system whole to magnetars with magnetic fields strong enough to erase credit cards from halfway across the solar system, we've journeyed through a cosmic gallery of extremes. These stellar titans redefine what power means in the universe. Some dominate through sheer scale, like Stephenson 218, stretching far beyond where Jupiter orbits our Sun. Others wield unimaginable heat, like Wolf-Rayet stars boiling away their own atmospheres at 200,000 degrees. And then there are the volatile ones, stars like Eta Carinii and P Cygni, blowing themselves apart in eruptions that outshine galaxies, only to rebuild and erupt again. Yet what makes these stars truly remarkable isn't just their individual feats, it's how they shape the cosmos around them. Every outburst, every stellar wind, every supernova scatters the building blocks of planets and ultimately life itself. The oxygen we breathe, the iron in our blood, the calcium in our bones, all were forged in the hearts of these giants and blasted into space by their deaths. In a very real sense, we are the legacy of stars too massive to live long, too powerful to fade quietly. Studying these extremes isn't just about cataloging cosmic curiosities, it's about peering into the universe's operating manual. The way a hypergiant pulsates teaches us about the delicate balance between gravity and radiation. The sudden dimming of a star like Betelgeuse hints at the chaotic processes preceding a supernova. Even the runaway velocity of a fugitive star like Zeta Puppis reveals the violent dynamics of binary systems. Each of these stars is a natural laboratory, testing physics under conditions we could never replicate on Earth. And yet, for all we've discovered, the cosmos always holds surprises. Could there be stars even larger than Stephenson 218 lurking in the dust-shrouded heart of the Milky Way? Might magnetars exist with magnetic fields so strong they twist space-time itself into knots? What about exotic relics from the early universe, stars made of dark matter, or black holes masquerading as suns? The universe has already shown us stars that defy logic, so who's to say what else is out there, waiting for the right telescope, the right moment, the right curious mind to uncover it. So the next time you look up at the night sky, remember, those twinkling lights aren't just points in the darkness. They're titans and rebels, survivors and time bombs, each with a story that stretches the limits of what we thought possible. And somewhere in the vast unknown, the next record breaker might already be burning, waiting to rewrite the rules all over again.